Right, then let's get started. All right, so we're fortunate to have Yuliy Baryshnikov, who will talk to us about dynamical systems and data analysis.
Yeah, like everybody here, right? So
Right.
yeah, thank you for inviting. And so it's a little bit of a talk. It's mostly where we want to be rather than where we are. It's sort of, but in general, the direction is the same as everybody wants to do. We want to observe some, dynamics, and we want to create some usable, hopefully some sort of discrete or some, like presentable model which doesn't sit in high dimensional space. I mean, which is essentially we want a discrete model of whatever we live with, and and we can form judgment of how we move on this model. So we want to sort of sketch the topology of the space, of the phase space we operate, and we want to understand rough dynamics there. And again, everybody's doing that in like various fashions. Like my kind of like desire was motivated by two things. Was, on one hand, I wanted to port some sort of mathematics, like some people want to port convoy theory. It's and these people are hugely successful. So I wanted to port some other theories maybe, and but also I sort of wanted to get rid. Like quite often we we rarely interested in the actual differential equations or actual dynamics. We mostly are interested in the properties of the stuff. We want to look at the trajectories and deduce properties rather than coefficients. Who cares about the coefficients? I don't care about the coefficients. I care about, what the trajectories look like, how they collectively behave, right? And that's, so the question was how we can, like we observe something like this, right? And we want to do something about it. And of course, you can, do various stuff. For example, you can do symbolic dynamics. You can like split into intervals, say, okay, so it's A and B and then C, then write down what you observe, like something like A, B, C, B, A, B, C, B, A, B, A, and so on. And, like, and you can look at this trajectory and, like ask various questions and then see that, it's really not really informative, and try to make a smaller subdivides, take smaller grid and look at the symbolic trajectory. This is one route, right? Or you can, just, look at the trajectories and try to, infer something. So you have, something like that, and, you look at this picture and they say, or, and probably I can interpret this picture. And again, this is a sketch. And this is the sketch I really would like to operationalize. So, I have some trajectories, and what I would like to say, okay, what, from these trajectories, I can probably infer that there is some, some attractor, right? And I have a bunch of trajectories which converge to this attractor, and there might be something in the middle, and there might be something outside. I don't really care. I might happen to discover it. I might happen to, it might happen that life will be bringing me close to this point. So I will be, of course, I will never get exactly to this equilibrium point, which is there. But I will get close enough to sit close to equilibrium point for a very, very long time and then notice it. And then I say, okay, you know what? I have the trajectory which sits there long time, and this long time I can declare to be my equilibrium point. Again, I don't observe it, but like I can, like this Antarctic, I didn't see it, but like I can believe that something there to counteract, right? So like this should be mass counteracting this huge continents in the north hemisphere. So that's how the people were sort of inferring that it's there. So again, like might be there, might be not, but like operationally it is there. I want operational stuff. And again, so I want sort of recover topology space and want operationally understand how I move through this space without writing these equations, without, just looking at the trajectories and see how they, interact between each other. And of course, we have this, like we have work which is going towards these directions, and of course we have things like tokens embeddings, and we have like Koopmanisms, and like various other I mean, it's not an empty field. And again, a lot of what I will be telling, this is like it's a rambling, it's a story. It will sort of will be mirrored or like parallel or resonates with some other stories. But again, so what I wanted to start with is this kind of my archetypal tool, which again started me like to think about it. There is this very beautiful result. It's Schoen, Jones, Siegel theorem, and it's very influential theorem, but it's unpublished. It was produced like 25 or 30 years ago, and there's a preprint, and like can easily find it. And it's like what it talks about. It talks about like Morse theory on a manifold, and so like you have a manifold something like this, and you have maybe some critical points here. So again you have this Morse function, just the height function, Morse function f. You have some critical points, maybe some saddle, some local minima to local maxima, and you have some dynamics there, some quasi gradient flow, which is whatever is good flow, and you can live with it and work with it. And what else you have? You have trajectories. You have trajectories. Okay, so you have this gradient. Sorry, this critical point. Let's number them for the future reference, maybe. And you have trajectories going between those critical points. So like, you have maybe one trajectory, but maybe there is another trajectory going from this critical point down, right? And there's like trajectory going this way and that way. So you have whatever. So this is the data. You have critical points. You have trajectories. And of course, typically, so generically, if you have two critical points, sigma and sigma prime, then you can look at all trajectories which start close to one point and end close to the other point, right? And those trajectories, because because of the all the systems are smooth, you wiggle a little bit this trajectory, you still start at the same point and end at the same point. You sort of you have this continuity. So it's a manifold. It's an open manifold. There is some nice structure. So it's a manifold of dimension which is equal to the you take the index of the bigger point, subtract the index of the smaller point, and subtract 1 because you factor by those trajectories. So for example, what you have here, you have this so the manifold going from sigma 3 to sigma 4 consists of 2 points, right? And the manifold going from sigma 1 to sigma 3 consists of 1 point, this one trajectory going here, right? So this is the trajectory. And of course there's like much bigger manifold going from sigma 1 to sigma 4. And this manifold is, by the way, it's already becomes quite interesting. So you have all these trajectories going from this point all the way up, and a little bit of thought gives you that it will be an open interval going like this. And the same with this trajectory. So if you look at all this trajectory going from sigma 2 to sigma 4, they form this open interval which is closes a little bit at some point, but then this interval sort of goes this way. So anyway, so this is like nice collection of data, and this is the starting point for the for this Cohen Jones Siegel theorem. And so like they again like they don't talk about the like the things which computer scientists should be talking, right? Like partial order set or just graph, right? They talk about category and whatnot, and this of course is off-putting. So they have a a category, and like of course the category is in this situation is just a glorified graph, right? So you have this graph, you have these critical points, sigma 1, sigma 2, sigma 3, and sigma 4, and you have these arrows, and those arrows, remember, those arrows are just the collection of trajectories going from this critical point to that critical point, and you have a lot of those guys, right? So remember, so this is just 1 point, this is 1 point, and this arrow is 2 points, right? And those arrows are segments, they're open segments, right? So what happens, so you can, and you can take the composition of the errors. So you can say, okay, so what is these two errors? It's just all the ways you can go from 1 point to the other through the third, right? You're not flying, from New York to San Francisco. You're flying through Chicago, right? So this is like it's completely different set of routes, right? So I can form this, they can, like for any collection of those arrows. So, A is collection of arrows in this graph, and for this collection of arrows, you can just form the product of these manifolds, right? So this product of manifolds of AK, and AK sits in this vector of arrows, and again, each of these MKs is so this is just some like reasonable compactification of this manifold MAK, right? So remember, like before we were looking at the trajectories which are going from from this point to that point, so not stopping on the way, right? Because there is no actual trajectory which goes exactly like that, right? Trajectory stops here. We just glue them together, right? But there is trajectory which is very closed, and those trajectories form an open manifold, and you compactify it, you get this something, some manifold with corners, right? So it will be just not an open interval, which is just manifold, but interval with the endpoints, which is manifold with corners, and like everything survives. If everything is nice and generic, all your data and Morse points, you can work with that. So you create, and like at each point seems to be it's very nice. Like you have a graph. To each graph you attach some manifold, something like a simplex, or maybe a little bit more complicated than the simplex, whatnot. And also you have this various various mappings, right? So remember, like in category theory, you have a lot of luggage, right? And a lot of luggage means, whenever you have composition of errors, and the composition of errors, it's also another arrow. So you have another arrow, and you have original arrow. So and always you have to sort of, whenever you have composition of arrows, you should be able to map it into the arrow which connects the endpoints of this long path. So this is sort of the extra structure you're obliged to provide if you have a category. So like in this glorified graph. Anyway, everything is completely formalizable. It's just, like computer science. When you write, like specification of Python, what is allowable there. So it's about the same level of complexity. And so anyway, so what you have to do if you have this, you have composition of those errors, you have to map there. So remember, this was 1 point, this was 2 points. So we have 1 point times 2 points. So we'll have 2 points. This composition will be just 2 points, and this thing is, is the whole interval. And again, contractually, we are obliged to map this into that. So of course there is a natural mapping of those 2 points in the end of this interval. Again, this is what we are talking about. There is sort of no big deal, and everything is pretty much formalizable if you are able to describe all these little perky manifolds attached to each of the edges. So again, so you have this, if you have this collection of mappings, you have, you should map it into M of A1, like you take the composition, you take this, this M, this big arrow which just takes the, like composes two arrows, and so, like for example, in our case, this M bar of A1 and sorry, A1, A3. So let's call this A1 and A3. This is 2 point because A3 is 2 points, A1, and we should map it into A4. And as I mentioned, it will just map these 2 points into the boundaries of this interval. So anyway, so we have this a lot of sort of gluing maps, and like when you have those gluing maps, then you have another pretentious construction which is called classifying space. And again, this is just tells you how to glue together all these pieces. So remember, to each arrow or to each collection of arrows, you have this some well-defined natural spaces. And then classifying space is just an algorithm, it's just a recipe how to glue together all these pieces. And they're absolutely natural recipes, right? So
are these gluing just concatenation?
It's not combinatorial anymore, right? So remember, so each arrow or each collection of each path gives you some topological space, maybe interval or some simplex or something like that, right?
Okay.
And so now you have this for each, so now you have remember, you have one arrow, another arrow, and this composition of arrows. Now you should be able to, to glue together various pieces, right? So this will be some topological space, this will be topological space, this will be topological space. You have to glue them together somehow.
Okay, thank you.
And this classifying space is just an algorithm. Again, it's completely algorithmic. It's finite algorithm. So if you have any way to describe those topological spaces,
when you say it's algorithmic, is it an algebra or is it less than an algebra of some kind?
Oh, it's just a recipe. It's just collection of identification. So essentially, what you say is that again for each path. So for example, for this path, you will have some topological space, right? So you'll have again, like remember there was two points, right? And you have this space, which is a segment, and then you'll then you do some a little bit of just gluing together. This gluing together is a little bit of work, but it's completely combinatorial work. It tells you what point to glue to what point, which points you're identifying. So if you know how to describe these manifolds, and again, this is a big if, this is the biggest if of the story in some sense. But once you have those guys, then identifying this is just absolutely, standard trivial recipe. It's very easy to do. And so anyway, so I to be frank, I just don't want to go into various details. So, but again, so those, okay, but I just write down. So just kitchen recipe of gluing different spaces. Finitely many of those gluings, right? Produces some new topological space, which is called classifying space. Of this topological, of this again structure, which is this graph with topological space. So anyway, and this output, this Cohen-Jones-Siegel theorem, is that the classifying space, this resulting space, will be homotopy equivalent to original manifold, right? So this is like, if you take very simple example, so this is your sphere, you have just two critical points, sigma 1 and sigma 2, and just one manifold, right? So just one arrow, A, sigma 1, sigma 2, one arrow, and you have M of A. Of course, it's equal to just this d minus 1 dimensional sphere, right? So this is d dimensional sphere. Then you have this equator. So the space of trajectories will be obviously d minus 1 dimensional sphere. And the construction essentially says, okay, you have the sigma 1, sigma 2, and you have this interval times, so this is sd minus 1 times interval, because you have an arrow. This is an interval. and then you have to identify this point to the whole disk here, this point to the whole disk here. And of course, this resulting space is nothing else but the suspension of this sphere. And of course, this is equivalent, homotopy equivalent, actually homeomorphic to your original space. So anyway, so this is some recipe which, again, it's hugely elegant theorem. And it was sort of, for years I was kind of puzzled why, nobody is using it the way the people use Conley theorem or, some, or Morse theory in persistent homologies, how like it's the tons of, like nice mathematical theory which were ported into, clearly abstract result, but, but not this one. And I was wondering then, started to think, okay, how you would do it, So kind of the whole sort of rambling is the desire to port this result into something operational for the needs of dynamical system or control theory, and the problems are are quite clear. So first of all, the recovery of these topologies of these trajectories can be hard. So remember we had this sphere. So if you look at this, remember this is one critical point, another critical point, and so the whole trajectory is going from one critical point to another. They can feel pretty non-trivial spaces by themselves. So like looking this, like again, and this is a simple case, right? So all trajectories going from sigma 1 to sigma 4, they form just an open interval, and it's clear how to compactify it. Life can be much less pleasant than this. If you have several points interacting, it's quite easy to construct examples even in two-dimensional manifolds and in high-dimensional manifolds. So this manifolds MA, they might be difficult. So this is one objection. Another objection is just how you find these critical points. I mean, everybody knows that it's absolutely impossible to balance your egg on the top. So it's impossible to find your unstable critical point, right? So you have to break your egg somehow to balance it. So if you have some something like that, even if it's not completely if there are some if there is stable submanifold, still like trajectories will behave somehow, even if you get close to it, still you will not getting. So this is the picture you will be observing. So can you live with it? Can you live without touching a critical point? I mean, probably you should. If the point is if your Lyapunov exponents are high enough, you have like strong repulsive components, you're never getting close to these points. It means you should ignore it. So in some sense, recovering of your manifold is not the ultimate goal. If there are points you will never visit anyway. So so you should lead by the trajectories. And so like ultimately what you will be observing is some collection of trajectories, and like the structure that there is some manifold outside of this these trajectories you observe will be completely irrelevant to you. So maybe your goal should be not to recover this topology of the manifold where you can be, but rather the domains of which you live in, which you observe. So anyway, so this sort of changed my way of looking, of looking at the problem, and maybe just try to see what how to look at it. So so alternatives is to we ignore the overall structure of the total phase space, again this whole manifold, and just focus on the trajectories we observe. So we'll have this so we won't have the whole the whole space, but we'll have this we'll have some part of the space covered with trajectories we can see, and we'll have some patches, and we'll look at those patches, how they overlap and how they intersect, and try to look from the look at the topology of the you look at the patches, patches or charts of some part, some maybe basin of attraction or basin of interest, and try to recover It's Topology and Dynamics. So again, it's like getting the goal much less ambitious, again, not to recover everything, but just, this is the trajectories we are given, and we'll look at them and we try to live by. So, and we don't have to go into this, like to be this maximalist about those, like we really need to know the, topology of all the trajectories connecting one critical point to another. We don't even know these critical points. So we have, but, still we'll need to live with some, so we'll need some apparatus, how we glue together. So like ultimately we'll still be working in the same paradigm. So we'll be seeing some pieces of our space given to us by some pieces of trajectories and some, like which we'll be gluing together. So we'll need some, mechanism of gluing. So there is slightly more general mechanism, again, like these classifying spaces which, Cohen, Jones, Siegel were producing, where ultimately, some specialization of more general construction of the classifying spaces of diagrams of diagrams of spaces. So I just want to like remind again. So there is another formalism, hugely hugely powerful. You can glue very easily new topological spaces out of old topological spaces. But it's not as widely known as it should be. It just remind you what it is. So again, we typically deal with partially ordered set. So we have partial order P. We assume it's finite. Like again, it works in much greater generality, but like we are looking at something which is finitary by definition. So like finitely many points, and you can compare it to them, right? So you have like P's and Q's, and which of them will be smaller than the others. And for each of this P, we'll have a topological space. X of P is topological space. And for whenever you have one space smaller than the other, you have a mapping from bigger to smaller. So you have P, which is bigger than Q. Then you have automatically some mapping. Let's call it P to Q from X of P into X of Q. So those are the data you need. And, so like just an example. So you have some,
Yuliy, I'm sorry, Yuliy, the P's are not necessarily cells, but there's some kind of topological space.
It's just some discrete things, right? Okay, so this is this is my partial order. This is an example of a partial order.
But the entries, the X of P's are just topological spaces.
Yeah, a little bit topological. Yeah, it's some topological spaces. Yeah, let me give an example, then we'll see. So assume you have M, which is covered by some open subsets U alpha, or UP. Sorry, we'll call it U of P. Okay. So we have finitely many. No, bet. Sorry about this. Alpha. And we'll take P to be just 2 to the power A. So all the subsets of A, right? Such that, P belongs, so I is in P if the intersection, you take the intersection of those alphas, where alpha sits in this I, and it should be non-empty. So you just take all this intersection poset, like you just take the, for example, if you have, if this is your M, and this is your U1, U2, and this is U3, then of course we will have this, 1, 2, and 3, and 1, 2 has a non-empty intersection, 2, 3 has non-empty intersection, and 1, 3 has non-empty intersection. But of course, no 3 have non-empty intersection. And you have the mapping. So and the and the partial order set by inclusion, but in the right way. So J is bigger than I if I belongs to J, right? So the bigger, right, so, right, if J belongs to, yeah, if I belongs to J, sorry about this. I was right, if I belongs to J. Yeah, and you have the mapping from the bigger to smaller ones, right? And those so yeah, and my, and U of I, it will be just the intersection of my alphas, alpha belonging to I. And, you know, if J is bigger than I, then it's intersection of bigger number of those vicinities. So it just, you know, like it just sits within. So all these mappings, so D, J, I is just embedding. So this, you know, so this is I13. Sorry, U13, and U13 is mapped into U3 and then mapped into U1. So you have this guy, you know, and you look at this partial ordered set, you know, like if I draw it in sort of in a better way, I'll draw it in a better way. This partial ordered set will be 1, 2, 1, 3, 2, 3, and this will be bigger than 1, this will be bigger than 2, and this will be bigger than 3. Right, and you see that, you know, there is a resemblance of this partial ordered set, what it looks like, with the circle which it's covering. And of course, you know, so the diagrams of spaces is new topological space which will be gluing somehow from those, you know, pieces, and how these pieces are interacting between each other. So you have this, you know, diagrams of spaces, then you can, you know, produce this like thing which is called homotopic limit, and again it's just like big word which essentially is just a kitchen recipe of gluing those spaces, right? So you have them like you have this space XP, and you have, you know, like maybe X of P prime. And one of them is bigger than the other, so you have a mapping, you know, like Q, sorry. If Q is bigger than P, then you have mapping from Q into X, and there is sort of way how to glue together these guys. And if you have several of those mappings, you know how to glue them together. So there is sort of, again, finitary constructions, which gives you extremely well-defined recipe how to, again, I will just maybe, how much time, how many things. Okay, I produced some formula. Maybe I'll just copy them.
You
so
have
this,
about 20 more minutes.
Say again?
You have about 20 minutes.
Okay.
A little less.
Okay. So anyway, so you can glue together. So this homotopic, you know, this is essentially, again, it's gluing construction. And giving new space out of all these XPs and all this attachment, all these mappings from P to Qs. And there is some like nice, it's very nice construction because there is like very nice properties. For example, if you wiggle, so you have this mapping from one space P into space Q, and imagine you just start to wiggle it. Right, so just homotopy it, just change continuously this mapping. So you have a mapping and you change it in a continuous fashion. Then your homotopic limit is not changing. It will have exactly the same structure. There's like huge robustness in this construction, which is nice. And you know, one particular example is that if all of these spaces, if all of these XPs are contractible, then, you know, essentially the problem becomes completely discrete. It depends only on the partial order, only how the spaces are, which of the spaces is mapped into which. Doesn't depend on the mappings at all. So you can completely forget your continuous component of whatever you had. You can concentrate on just purely combinatorics of what you lived with.
But this will mean that you have a very well-defined notion of constructibility.
That's right, yeah. So like, yeah, now I have completely discrete, I have a simplicial complex which does not depend in any way on my sort of continuous components, on my spaces x of p, and how this space x of p is mapped into x of in x of q.
And is that problem easy or hard?
What's the problem?
The problem of detecting if a space is constructible in your sense.
I mean, well, if it's constructible, it's hard, unless you stipulate it in some way, or unless your problem, sort of the structure of your problem.
No, I mean hard computational.
I mean, like the topology of the space in general, it's completely a hopeless proposition in general. But you always live to, in some special part of the world. So, sort of, James. Sorry, I'm a bit hard to answer this particular question just in general.
Okay.
Yeah. So, but like again, so like very special case and standard case is the so-called Nerf lemma. So anyway, let's move back to dynamical system. So what I want, so this idea, so idea is just, again, as I mentioned, we'll be just looking at the trajectories and try to identify them. So, we'll have some, trajectory going this way. And again, by looking at trajectory, I don't mean to sort of like computing it very precisely. It's, just observing it. And we'll see some trajectories behaving like that, and I say, okay, you know what? They go together for a long time, so maybe we'll just, can find. So this is the piece when they are fellow travelers. So maybe we can find, declare, so this is a tube where this all three trajectories live together. So this will be our smaller piece, and we'll be following, we'll be following this piece. We'll declare this piece as sitting in each of these. So this is a red chunk sits in each of this big long chunks. So we'll be using this as as this mapping of this red piece into this big black pieces, and then we'll be using this combinatorial data to glue them together and to construct new spaces which will be glued out of these trajectories. And if we can observe just few trajectories, we'll get one space. We'll get more information. We'll maybe filling our space. So it might happen that we'll have some trajectories which go this way, maybe go on this way, and go that way, and then we'll run into some trajectory which just hovers for a long time, close to has a long overlap with each of those three trajectories, and we say, oh, maybe we just have to declare, there is some fixed point or whatever, conceptual fixed point, which is just a long piece of trajectory which sits there and doesn't go anywhere, right? So we'll be using some tubes around those around the observed trajectories, and we'll be using some disks if we see the trajectory which doesn't move. If we cannot form, if the velocity is low, then we'll just declare this piece, just the disk around this point. Our set, and if it's moving, then we'll declare a tube around this trajectory. So we'll start building this. So build those spaces of xp around trajectories. So tubes, if moving, just disks. If slow, and by the way, so maybe some of you are just asking, so you're looking at your trajectory, so maybe just the whole thing just brings us back to essentially tachyons embedding. You're looking at tachyons embedding, you look at a piece of trajectory, and then you're trying to reconstruct the topological space out of those pieces. But important that we allow intrinsically the pieces of trajectories of very different length. So it might be long piece and short piece, and we use the short piece because it's common, it's shared by the long trajectory, long piece of trajectory with some other pieces. So there is no fixed window. So like important departure from like tangents and windows, etc. Trajectories of different lengths. Anyway, and we'll we'll build some pieces. Of course, again, we need some regularities.
Can I ask a quick question
Uh-huh.
here? I mean, if you go back one slide,
This one?
the one yes. So I'm a little lost with the trajectories at different lengths. I mean, you drew trajectories at different lengths,
Uh-huh.
but then you kind of hashed with the red. So there you kind of, you then put a scale on of how long you were going to compare those different trajectories, right?
Right. So what I would like to do is to say, okay, so I also introduce the trajectory like this. Oh, sorry, I should change color. Introduce the trajectory which looks like that, and trajectory which looks like that. So I will continue the piece, consider the pieces of those trajectories, which then will run concurrently. Then I can compare them and say, oh, they're very close to each other.
Okay.
So they belong to
But
the
that
same.
is kind of a form of windowing. I mean, I'm not claiming you're getting back to talking.
Right. So there will be there will be windows, but if you like, adaptive windows. So
Okay.
I'm considering this trajectory, this long trajectory. It will be at some point in my space. This red trajectory will be another point in my space, and I will be mapping one into another.
Okay. No, I think I've caught up then. Okay. Thanks.
And yes, we'll need some regularity conditions. So again, like what we'll need, we'll do the tubes around pieces of trajectories of different, of which we observe. And again, there is a lot of things which are unclear to me yet. But what can happen is that right. So as I mentioned, there will be like pieces of trajectories of different, which will be diverging, and you will be creating some tubes around them. Right, so we'll be creating maybe some tube around this trajectory and some tube around that trajectory, and of course you will be forced to take the intersection of them. So you'll be forced to take these shorter tubes, behaving, like to taking the overlaps, and also you will be forced to have the, some balls around the trajectories which are not moving fast. And you will need the conditions you will need are that, of course, the intersections of tubes will be tubes. That's not very difficult. But another thing you will need that if you have the tube intersecting those balls, then this should be affiliated by trajectories with the base being contractible. So this is some technical conditions which probably will deform as the investigations continues. But conditions. So we need the the intersections of tubes and disks should be affiliated by contractible families of trajectories. Okay, so let me just the rest. I'll just spend a few minutes just discussing a couple of examples. And again, there's not really computational examples. If you look at the standard, what will this construction result if you have the standard dynamics on the spheres? You have two critical points. We have this, one-dimensional or whatever dimensional family of trajectories, and so what you would expect is that you have some vicinity like that. We'll have some vicinities. We'll have some tubes like this, and and you will just build the interaction, the intersection of them, and again, this trajectories not necessarily should go from the whole length. It might be just going some partial length and so on. So it's quite easy to see that like essentially, if you manage to capture, if you found a trajectory which is hovering close to this unstable point on top, then essentially you will recover your sphere. If you somehow miss this point, then you will recover just the basin of attraction, but it probably will tell you something. Maybe this point, this top of the sphere, this North Pole, maybe it's something you just unable to notice. Maybe it's not there in some sense. Like from technical perspective, from the engineering, from the application viewpoint, maybe it's just absolutely fine to ignore this top as long as it's not presenting itself to you. Anyway, so let me just go to something which I feel more excited about. So how what it will look for the case of Lorentz attractor, and so we know how to sort of stylize. We all know the stylized picture of the Lorentz attractor, and you have this template. So you have this so like bifurcation. So orbits can go to the right and to the left, and if they go to the left, then they loop back and they go to the whole thing, and if you go to the right, then they also go back to the whole thing, right? So and you have this trajectory. So like you have trajectory starting, say, here. It will go maybe this way. Maybe you observe trajectory starting here. It will go that way, and then loops continues. Okay, it's a bad trajectory. Sorry about this. Maybe it continues going this way, and maybe you'll start here. You go trajectory going this way. Or maybe there is trajectory starting here, which is going that way, and then it, continuing something this. So you will be observing those trajectories, and it will be, producing this stylized picture of your, of your thing. And essentially, like again, you don't have even to look at the three-dimensional trajectories. You have to look at the one-dimensional projection, and essentially what will happen is just what we're doing before. So we'll be like taking those subintervals and saying where from those subintervals you are going. Like if you're hitting this, you are here, you're hitting at one side of the divide, the other side of the divide, and from each side of the divide being A or B, you can go back to A or B simultaneously. So I was looking at this picture, and of course the the resulting topological, the diagram of spaces will produce something which is homotopy equivalent to this picture. So you have this branching point, you can go right and left, and then this will be merging point. So the topology of the space will be it will be a wedge of two circles. And then I started to play with these pictures to produce those symbolic trajectories. It's not what I was seeing. So it was sort of, the picture was not what I expected it to be. And then I realized that, in fact, something different happens. So like the correct picture was not something like that. The correct picture was, what happens if you just take this bifurcation point and pull it up? Then it's, splits into two pieces, right? So we'll have piece on the left, and you have piece on the right. So altogether, the construction, so if you take this part, okay, let me just copy this. And, oh no. Not good. Okay, sorry, let me undo it. Just redraw this picture. So what happens here is that you have bifurcation points here and there, And here you're looping back from this direction, and here looping back from that direction. And if you look at this picture, you see that topology of the space is not the wedge of two circles. So this is homotopy equivalent to this picture, which is homotopy equivalent to the wedge of three circles. And that's exactly what you observe, because if you do this discrete dynamics, then you can easily see that like from the same level you can go both down and you can go up. So here you have 2 points going up and down, and you have the same way you have points going up and down from here. So altogether, like you recover your topology just by looking at the pieces of trajectories, of one-dimensional trajectories in your in your observed in just your observed dynamics. So you look at the samplings of your dynamics, you consider pieces of trajectories of different pieces of different length, identify them, and you can recover, effectively you can recover topology of the space and the dynamic on the space, because it tells you, okay, so at some point you will be branching, and of course you don't know exactly, there is some intrinsic stochasticity there, so there is branching points, but the number of branching points is actually not one, as in this picture it is two. It happens in different pieces of the space. So like altogether, it turns out that you can recover rather, like using this approach of just like looking the piece of trajectories, identifying them, using these gluing procedures, you can recover rather subtle features of your space. Okay, last point is a little bit,
And Yuliy, you're kind of out of time, so let's.
Yeah.
Okay.
Just Dan will kill me if I don't mention hybrid dynamics, so I have to. It's I just want to emphasize that this picture, these templates for the templates for this Lorentz system, in some sense they exactly equivalent to this hybrid dynamics. So this merging of trajectories. So of course this is template, this is a caricature. In the hybrid dynamics, we just have the actual merging of trajectories coming from different spaces. So in some sense, we don't need to reinvent new theory. The old theory, the theory which works for smooth dynamics, can be directly ported, it seems, to the hybrid systems. So, okay, a couple more remarks, but let me stop here. Thank you.
Thank you. Other questions, comments? So let me ask a question, because so I'm actually trying to think about maybe on a too practical level too quickly on the construction of the space, right? So, an alternative possibility would be to just collect the data points on the trajectory and then say, okay, here's a collection of points that I have, and now there's going to be some kind of topological, combinatorial space that I've built out of all those collection of points and distances between them, right? Because you are eventually going to have to measure the distances between the.
That's right. Yeah. You have to, right.
And then to try to put the topology on the dynamics on top of that space that you've constructed. So what you're doing is somehow trying to keep the trajectories information at the same time while you build the space. Is there and there's a dial that would go with that. I mean, you could also think of saying, I'm going to look at all points and their images and compare that to points and images and make a space with that extra piece of information.
I think again, like imagine you don't have this, you typically imagine you're given a system of equations and you do the dynamics in the space. Like imagine you don't have it. Imagine you have this projection. You just have this. You have just this plot right here. Mm-hmm. So there is some underlying dynamics. It is somewhere there. You just don't want to recover it. You don't even want to build this manifold. What you want to do is say, okay, so I want to. So this. I have this chunk of trajectory, this chunk of trajectory, they're pretty the same. I can just glue them together. They're like within one tube. There is this chunk of trajectory and this chunk of trajectory. They're close enough if I, I can identify them within one tube. So I can build those identification slowly, and then I can, but there will be also branching points. So, from here, from here I can go up, and from here I can go down. So I will identify those branching points, I will identify these pieces, and then I will construct my, in this case it will be just a graph, because there is no stalling in some sense. And from this graph, like from this branching graph, I can claim that it describes what I observe. I don't know my manifold. I don't know the dimension of my manifold.
Right.
I don't know what is, like if I want to patch, so if you look at this, if you look at this picture, we know there's something here and something there. We will never discover it. Right. So there is deficiency. However, if I observe only this graph and I want a model for this graph,
right,
then what I claim, this is good enough.
Right.
I'm not disagreeing with that. I'm kind of asking about, because I like the idea. I'm just asking, and that's why I said maybe I'm being too
Right.
practical too early. The other extreme would be to say, okay, I've got the collection of points, right? You have all your data points, and now I'm going to build a space. There's no reason you wouldn't expect to reconstruct all of R3, and then put dynamics on top of it, because I do have all the trajectories, right? And the other extreme is, which you're not doing also, which is to use one trajectory and say, well, I've got my space is just one long is R, right?
Right. So no identification is still right.
So there's a tuning parameter there, right?
Absolutely, right. Yeah, and I didn't explore that. Definitely there should be some, absolutely clear that there should be some filtrations. You can make tubes longer, which will give you one type of, gluing. You can make tubes wider, which will give you another type of tuning. There are plenty of things to explore. Right now, I'm just playing with the examples.
Okay, right. One quick question, if there is another question.
Yuliy, can I ask quickly? I mean, the worry I really don't understand a lot of what you said, but the worry here is you're insisting that the intersections are going to have these contractible, there are going to be tubes that are contractible.
Right.
In my data, if I don't know any better, almost any data, any observation I make is going to yield that kind of a contractible property, because I won't collect enough data to see otherwise. And so, shouldn't I worry that I'm not going to see, the Lorentz thing is a Cantor butterfly. It's not a real butterfly, and you're not going to capture they're not going to capture the.
No, I mean a lot of right. So I'm not telling you anything about the sort of the I'm not going to present you any periodic trajectory. I'm not going to tell you, okay, so this is the structure of the set of structure of the set of periodic trajectories is such and such and such. I will not discover all these counter sets. The question is, so is your task to discover those counter sets, or your task is just say, okay, this is what my system looks like. It has branching points here and there. And again, I as an engineer would be sort of, it's nice to know that there exists a trajectory, periodic trajectory, which is sort of unstable, in any possible sense. So
your guess is that the attractors will stand out in
the attractors will be attractors will stand out, exactly. So if you have something stable, you will see it. It will manifest itself, and it will be manifesting itself. There will be some subcomplex of your. This is like one of the comments. There will be subcomplex of your, of your diagram of spaces. There will be sub-diagram which will be, again, sitting there, and you will be seeing it. So, and of course, it's natural question to ask, okay, so is this thing, we have a potential attractor, this circle. Is it a thing attractor? No, it's not. We can see it. This bifurcation point is not sort of removable. We cannot purify out from it. And you can, again, there's a lot of tunable parameters, and you can play with it and say, okay, so like within the resolutions which we are interested in, there is, it's not an attractor, and there is nothing, again, it might be some periodic trajectories, such the domain of attraction, this periodic trajectory, stable periodic trajectory, the domain of attraction is extremely thin, but we just don't see it. It doesn't exist to us. So we should be Berkeleyians in this respect, like something which don't observe, we shouldn't care about it. And we couldn't, again, like imagine the world without equations. Anyway.
I'm gonna stop this because we need to go on. So let's thanks Yuliy again, and let's start up at 3:10 with Marcio. Okay, so a 4-minute break. And Yuliy, we should definitely talk about this stuff. This is very interesting.
Gladly, thank you.
Can you give up the screen?
I'm trying to, now my mouse died. That's
okay. I think I'm killing you.
Okay,
oh, I
good.
killed you.
Yeah.
That's the power of being the host. Marcio.
Let me try.
We killed the opportunity for anybody else to have the screen now, and then I won't know how to fix it.